Well, let's see. This subroutine that I want to show you here is a demonstration of how you can delay for, say, 5 milliseconds. So I've already written the main program with a call to the subroutine. And down here at the subroutine, we're going to write the looping to delay for 5 milliseconds. This will be a fairly long delay. So we need to calculate. Let's see, we'll do a calculation right here. Let's see, this is 5,000 microseconds, which is equal to 5,000 cycles. So down here we're going to have a loop that looks something like this. Let's try, how about a subtract immediate word x comma 1. So this will decrease x by 1. Branch if not equal to delay 5 milliseconds 1, and that'll be up here, delay 5 milliseconds. Notice the name I'm using here in the label is the same name as the subroutine with a number 1 appended to it. This allows us to have labels that don't repeat throughout the entire program. This label here is like this label, so it's guaranteed that no other subroutine or code will have the same label if I append numbers at the end like this, 1, 2, 3, 4, 5. Okay, this no-op has 1 cycle. Subtraction has 2 cycles. And the branch, when it does branch, is 2 cycles for a grand total of 5 cycles per loop. And I got those numbers from the book. In the table, there's a table of instructions, and it tells you the number of cycles for each instruction. So we have, again, 5 cycles per loop, and that would mean we would need 1,000 loops. So we have to load x with 1,000, and to do that we're going to say LDI. You can't load x solely with 1,000 like this. That doesn't fly. You have to do the high portion and then the low portion. But, well, how many thousands are into x high and how many into x low? X high starts at 256. So if you take 1,000 and you divide by 256, that will be the portion in x high. And the portion in x low will be the remainder of this division going into x low. So again, for every 256, that is 1 x high. And this, I think, would be 3 here, if I did my math right, going into x high. And then the remainder will go into x low. I'm not going to do that math myself. I let the computer do it with a divide here and a remainder here. So now x is properly loaded with the value right there. All right. So we have a load, blah, 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 blah. Just checking the code. We should have a push. And we're going to do push x high. Yep. Push x low, and then a pop x. Make sure we do this in order. POP x high, like this, in that order. Well, let's see. We have the call, we have the pushes, the pops, loads. All right, looks good at first glance. I'm going to build it. It built, and the next thing we need to do is to simulate this. Okay, so let's try the simulation. We're going to put a breakpoint right here. We're going to run the R call and see how many cycles it takes. We're going to say debug the F11. It's right here. Okay, it says to select a debugger, so we're going to pick the simulator. That's good. Come back over here and try that again with the F11. Alright, things are getting set up. And let's take a look here, see what's happening. Alright, so we're right here, ready to do the call, right up there. I noticed that the frequency is 1.2 megahertz. I want this to be 1.0 for the ATmega328. So that frequency is correct. The stopwatch is set to 0 microseconds. And if I hit the F11, it's going to bring me into here. It's going to go line by line, and I don't have that much time to waste here for this. So I will hit the F5, and it's going to do its thing here. It got back to the R jump, and then we come over here to the stopwatch and take a look at this right here. It looks pretty decent. It says that the stopwatch is at 5,015 microseconds. Why the extra time of 15 microseconds? Well, we have the 5,000 correct. The 15 microseconds is because of the things like the push, the loads, the pop, and the return, which are not in the loop. So if the 15 microseconds is not accurate enough for you, if it's too long for you, we can decrease. 3 loops would do it actually. If you because it's 5 microseconds per loop, we could decrease this by a 3 here. Something like that would work. But I'm going to leave it as is, and for me it's fine.